So before we get started, raise your hand if you guys are currently deploying a monolith to production. A few people, OK. Now keep your hands raised if you want to take that monolith and move it to a microservice. Cool, that's good. And now raise your hand if you guys are currently deploying microservices in production today. Oh. Now keep your hands raised if you want to move back to a monolith. All right, cool. Well, today we're going to be talking about how to move from a monolith to reactive microservices. I'll go over how people typically move from a monolith to microservices, and I'll propose an event-driven architecture and the wins and woes of this kind of system, and we'll end with a nice demo. A bit about myself. My name is Anand Patel. I'm the lead engineer here at Runnable, and I graduated from Georgia Tech with my master's degree in computer engineering, and I started my career at NVIDIA writing low-level software kernel drivers. And from there, I moved to large-scale distributed systems. Now, surprisingly, they do have a lot of things in common, mostly programmers. But for the past 4 years, I've actually been working at Runnable, building and designing reactive systems. Now, I have to put this warning out there. This talk contains grossly oversimplified code and is not intended for use in production. Now, with the warning out of the way, today, we want to make a microservice. We want to make a service. We want to make thebestmusic.com. Now, on this website, what it should be able to do is you should be able to listen to music and also comment on it. And lucky for me, I have all you smart guys here in the room to help me build it. So let's get started. So we spent some days, and we built this thing. It has a music player, comment engine, emailer, video hosting, database, all in one gigantic monolith. Now, let's look at some example code from this sort of type of system. Let's take a look at what happens when a user comments. We have a parser which normalizes that data. We have a database connector which saves that comment in the database. And we have an emailer which sends a thank you email. Pretty straightforward. And I think this is ready to ship to production. So we go ahead and ship it to production. And there's no hitches, besides the fact that it takes 10 gigabytes of memory on boot. But whatever, we can ignore that for now. And this is running for us fine, until one day we released the Rough remix by the DOGG. Now, on this day, our site went viral, and we had to start scaling like crazy. And it became pretty expensive, because you remember our monolith takes up 10 gigabytes of memory every time for every instance of it. And we needed to do something better, because along with all these new users that came in, they were asking for more and more features. People wanted to add emojis in their comments. They wanted to support Markdown in their comments. Or they forgot their password and wanted password recovery. And so we started adding all these features to our monolith. And it actually became more and more dangerous, because one small change could cause the entire system to go down. And that we couldn't accept. That was because our competitor, overplayedmusic.com, was always up, and they were shipping features like almost every day. So what do? We heard about microservices, and so we decided it will help solve our problems. So we go back to our monolith, and we tear it down into small functional parts. The database, the parser, the emailer, they all get their separate microservices. And for everything that we can't functionally break out, we stuff it into our master service, aka the microlith. Now, what would code look like in this type of system? Well, now instead of calling the calls directly, we have RESTful clients which interact with each of these microservices. It's pretty identical to the monolith code, right? However, we've introduced a few problems. For example, what if the email service goes down? Now, when a user tries to comment, he's greeted with an ugly 500 error. And he's angry because he couldn't be the first one to comment on this new music. And typically in these kinds of systems, when one service goes down, the rest of the services that are dependent on it go down with it. Or we bubble up some error all the way back to the front end. What about another example? Say the emailer is just slow because it's bogged down. Now when a user tries to comment, he's stuck looking at a spinner just because we couldn't send him an email. And he gets really frustrated. Now, of course, I'm sure this will never happen to any of us, because we write perfect code, we have 100% test coverage, we catch and handle all of our errors, and have sane timeouts for all of our HTTP clients. But what about in this scenario? We realized that in this app, nobody really eats emails anymore. We need to do something more hip. So we decided we wanted to send thank you selfies on Snapchat. Now, nobody here knows how Snapchat works, so we needed to hire a developer specifically for this task. So we hired a Snapchat developer, And since we have microservices, all they had to do was write this Snapchat microservice and add one client line to the comment functionality. Easy, right? Well, it turns out our Snapchat developer lives the YOLO lifestyle and tests his changes directly on production, an authentic prod cowboy. And now we've actually broken our critical path. Nobody can comment on the site anymore. Now, microservices promises fault-tolerant, resilient systems. But without significant code investment, we actually never get to see these benefits. Now, we got to this kind of system thinking in a linear way. When X happens, we want A, B, and C to happen. But what if we think about this problem in a different way? Enter reactive architecture. One service should not tell another service what to do. Instead, these services should be smart enough to know when something's happened in the system and react appropriately. Now, what do I mean by that? Remember our example? The microlith should not be telling the emailer to send an email, or it should not be telling the parser to normalize the data. Instead, these services should know when a user has emitted a comment and then respond appropriately. Now, what would an architecture like this look like? Something like this. As you can see, our microlith has shrunk considerably now that it does not have to handle talking to the other services. But the major change here is our message bus. We now have a message bus that connects everything, and its job is to pass messages around. It knows who's subscribed to what events, and knows who's publishing those events, and it routes it correctly. This becomes the heart of your application. Now, there are a few services that do this already. Amazon SQS, Kafka, and the one we use here at Runnable is RabbitMQ. Now, let's go back to our code example. Now when the microlith gets a comment, it emits an event called comment received. And it passes this to the message bus. Now the message bus knows who subscribed to this and sends the messages accordingly. So the emailer gets this message, it sends a thank you email. The parser gets this message, it normalizes the text, and it also emits event, comment normalized, which the database picks up, and then we finally save the comment. Now, remember our Snapchat example? How about that? Well, the Snapchat developer just has to make this service, and it doesn't actually have to change the monolith. It just listens for a comment received and does what it needs to do. It sends a selfie. Now, one thing I want to note here is the event name, comment received. It is very important that you never describe the intent in your event name. Event name should always describe what has happened in the system. And if you do this, you can truly decouple these services because they don't know what's going to happen when they emit the event. So let's talk about what makes the system really great. As you saw from the example, the services don't know that the other exists, which makes these services truly decoupled because they're not describing intents in their events. They're only saying, hey, this happened. Do with it what you will. And with the Snapchat example, you saw that you just had to make your own service. You did not have to change code in any of the other microservices, which lowers the risk of adding new changes to our system. Now, since these services can go in and out, they can crash as much as they want, they won't bring down the rest of the system. Each microservice is independent, which allows for the system to gracefully degrade. And when these services do come back up, we can actually send them the events that they missed, allowing them to self-heal themselves and get themselves back in the right state. And now I think you've noticed that these services are basically just consuming events and emitting events. What we can do is we can take that as a spec, give it to any developer, and they can implement it. And they don't have to know how the rest of the system works at all. And this promotes independent team. Now, of course, with all architectures, there are some trade-offs. So it's time to talk about some of the woes. First things first, the message bus becomes the single point of failure. If this goes down, your entire system comes to a grinding halt. So we want to make sure that our message bus is highly available and we're following all the best practices for this. And we also want to make sure that we're persisting these messages, whether in a database or on disk somewhere in case of catastrophic failure. Now that we have all these messages flying around, it becomes extremely difficult to debug these kind of situations. There's not one place in the code where we can look to see flow. We can't see A, B, and C happen in sequence. So we need to make sure we have really good logging practices. We want to log every message with a transaction ID, who's published the event, and who's consuming the event. We also want to make sure we have up-to-date documentation of these events and the flows. If you've done number one, it's relatively easy to make this documentation dynamically update itself. Now, consistency also becomes a big problem in this kind of system. Because we're dealing with async messages, you can never guarantee at what point in time these events are actually going to be processed. However, we can ensure eventual consistency by doing two things. you want to make sure that first, your message bus guarantees at least once delivery, and second, your event consumers are idempotent, meaning if you send the message twice, it will still be in the correct state. Now, it's cool to talk about these newfangled architectures, and it's another thing to actually use them. Runnable is actually built on this event-driven system, and we've seen a lot of benefits. We were able to implement new features with little risk. Before, we had a lot of regressions, which caused significant portions of our application to go down. But when we moved to this new stack, we were able to add features more rapidly and reducing the risk of bringing down the rest of the system. And since these services don't have to have error catching inside of the clients, or they don't know about the rest of the applications, we've significantly reduced the complexity and the code required in each of these services. And it's also actually helped us with unstable endpoints. We've actually been working with Docker since the 0.3 days. And we've been through all the API changes, all the econ resets, and socket hangups. And we started when we had the original microservice architecture. We just had an HTTP server sitting in front of this guy. And when Docker went down or held the sockets, this service would handle it. It would still return the 500 errors. And we realized when we had 10,000 requests happening at the same time, this guy just choked up. And that was because it turns out ports are actually a scarce resource on servers. And when you're running 30, 40 microservices on the same server, you'll find you'll quickly run out of ports if you're holding them open. And since the message bus now takes care of most of this traffic, we significantly reduced the amount of TCP connections that we're holding open. And one unsuspected benefit that we got out of this was for new hires. Before, when we got a new hire, they were fixing boring bugs, writing tests, or reading outdated documentation. Today, we can actually give them a service to write themselves, and they can push that to production, and they'll feel accomplished, and we know that it won't bring down production. So, I talked a lot about this service. Let's see one in action. I'm just going to go here. I'm using Docker Compose for this example, so we're going to bring it up. Boop, boop, boop. All right, that should be good. Now, this is actually an interactive example. Whoever has a laptop can log in, and if you visit reactive.runnable.com, you have thebestmusic.com. And here, you can write your comments. Hey, how you doing? And now what this is doing is it's sending an event to the backend, and this backend server is publishing comment received inside of our RabbitMQ over here. And just like an example, we have an email service, and we have an email service, and we have our parser. Our parser is actually our normalizer. It just normalizes the content down to 100 characters. If it's over 100 characters, it will just truncate it down to 100 characters. Very simple. And so if you want to see how fault tolerant works, let's kill the let's kill the database writer. Demo. 1 second. There it is. Let's kill. Oh my god. All right. Now, nice, it's killed. So let's see. All right, as you can see, database is down, so it's not saving anything. And if we just bring it back up, wait a few seconds. Live demo, refresh the page. Yep. It came back. Those are the messages. Nice. Now, like I said, you can actually start adding services to this RabbitMQ. I had the link here. If you clone this repo, you can actually start the service, and now you're connected to our Rabbit, meaning you'll also get the message. So if you start typing something, this service, immediately gets that event, and this can crash as many times as it like, and it's not going to affect, this messaging system. Yeah. Cool. All right. So, you guys can play around with that if you guys would like, but do you guys have any questions? Yes.
When you get micro monolith now, right?
What do you say?
The micro monolith.
Yes.
Or micro life.
Yeah, micro. Yeah.
And how would you kind of design the parts where you
Right.
It has to be safe.
Right.
But maybe you have a bigger system, a bigger company, and you have to kind of reuse the user service. That's called user service, right?
Right.
So how do you handle that?
Right.
There you cannot just say, okay, do it eventually.
Correct.
That's the question for the report.
Okay. So there's like two ways you can solve that. You can solve it, with traditional HTTP clients. You don't have to fully go, fully reactive. You can still have the clients where when you get a request, you can, communicate with the with your auth server, your LDAP, whatever you want, and ensure that you have the correct authentication. Or you can do sort of a proxy message where you would say that you send this message to an authenticator, and that authenticator would authenticate the message, add whatever data it would need, and then resend the message to the actual target that it was intended to go to. Sort of like middleware for events.
But then the microlith would still have to kind of be paused, idled, so that it waits for another async message to come back.
Correct. Yeah.
Some kind of response, some promise that it waits, right?
Correct.
And you put like
Right.
sync semantics over async infrastructure.
Right. So yeah, you would have to wait. That's one of the downfalls of the system. It is eventually consistent. It's not consistent right away. So that's one of the trade-offs that we made.
Have you guys run into any race condition types of? Have you guys run into any race condition? Have you all run into any interesting race condition events because of consumers having to be?
I see. Have we run into any race conditions because our consumers are idempotent? So how we deal with race conditions is, even though sort of these are async messages, we usually, if we need something to happen in sequence, we emit those events. So as you saw in our example, if we needed these to be in sequence, we would actually listen for the event that would emit. So in this case, comment normalize, and that would actually save the comment. It wouldn't actually listen for the actual comment received. So if you need something to happen in sequence, you'd have just the sequence of events that you want to listen for.
What I see from a more of an infrastructure perspective, there is a greater underlying question is network. When you have a lot of these service level dependencies communicating with each other, either by RabbitMQ or whatever, you are communicating over network. However, in production or in any infrastructure, network is almost the most unreliable component than your hardware or anything.
Right.
So you are placing your faith on an unreliable component called network. So how is this actually more beneficial? Well, if we're using a more traditional monolithic approach, all this communication happens by process, in the process communication, or by a stack in the CPU, which is more testing and reliable since hardware actual failure is not that common as network failure.
Correct. So his question was, the network's unreliable, and other methods are trained to handle these situations. How does this basically system react when networking issues happen? So one of the cool things about RabbitMQ, let's go back to our architecture. One of the cool things about RabbitMQ is they actually have to get around the networking issues, they have two things. Whenever you publish a message, it has guarantees that the message was published, and that means it's persisted onto disk. The process is only validated only once it's saved onto disk. So this process will continuously retry until it's known that the message is on disk. And on the other side, since RabbitMQ guarantees at least once delivery with confirms, RabbitMQ won't release that message from disk until it's guaranteed that the server has processed it and acknowledged that it received the process. So basically, we deal with the networking issues by having exponential backoff retry processes in both the consumer and the publisher.
However, compared to traditional ways, if you have load balancer which distributed to a bunch of these instances of application, so that if one of your network or one properly partitioned network, if a set of the server is down, the retry will fail and then will route to a healthy node. However, if part of the network is down, then you didn't retry, you never reach it.
Oh, right. So you can actually have more than one of the same worker server. So you can have like 20 of these all on different nodes, and they can communicate with the same RabbitMQ Or you can have a replicated RabbitMQ across multiple data centers. And so if this side goes down, the next parser will parse the data. So these aren't like single. These aren't single. It looks like single, but this can be scaled and scale, web scale. Any other questions? All right. Well, thank you very much. We'll move on to the next.